There's been nothing like OSIRIS-REx in NASA's repertoire. I like to call it the Daredevil spacecraft.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Today, I'm joined by Dr. Scott Sanford, an astrophysicist with nearly 40 years of experience at NASA and who has been part of every sample return mission since Apollo. In 2023, after a grueling 7-year and 7.1 billion kilometer journey, Dr. Sanford and the OSIRIS-REx team brought back a 4.5 billion-year-old sample from Asteroid Bennu. Inside, amino acids and nucleobases, the very building blocks of life. These organic molecules don't exactly prove that life is out there, but they hint at a universe which is rich with the ingredients required to spark it. A universe which is primed for life. In this episode, Dr. Sanford speaks about his journey from the Stardust mission to OSIRIS-REx, the mission's challenges, successes, and its implications on our search for life beyond Earth. Join me in vivo with Dr. Scott Sanford on the building blocks of life on Asteroid Bennu. Dr. Sanford, you occupy a very unique position in the world of space science, and that's the fact that you've been a part of every NASA sample return mission, except for Apollo, no fault of your own, including the Stardust mission, Hayabusa missions, and now, of course, OSIRIS-REx. And for that work, you've been honored by having an asteroid named after you. It's asteroid 16035 SA Sanford. But it's not that asteroid that I want to speak with you about today. It's asteroid Bennu, of course, which was the target of the OSIRIS-REx mission, of which you recently retrieved a sample that's 4.5 billion years old and has the building blocks of life on it, amino acids and nucleobases, the sort of result that makes molecular biologists like me super excited. And that work has now significantly contributed to the idea of panspermia, or the fact that asteroids like Bennu might act as vectors for depositing these building blocks onto Earth and perhaps elsewhere in the universe. But before we get into the results of your most recent papers, can you bring us back to the very beginning? How does somebody end up working for NASA and ultimately becoming a world leader in off-world samples?
Well, I can only talk about my experience, of course, but I have always been interested in space for my whole life. And when I went to graduate school at Washington University in St. Louis, I did my thesis on studies of interplanetary dust particles that were being collected by NASA U-2 airplanes in the upper stratosphere. So we were actually sweeping up dust as it was coming in out of outer space. And I studied those. So those are like little miniature meteorites. And then as another part of my thesis, I actually studied actual meteorites that fall to Earth. And after that, I got hired to NASA Ames to do a number of things, but partly to set up what's now called the Astrophysics and Astrochemistry Laboratory here, where we do a lot of experiments to simulate environments in outer space, in particular to try to understand what kind of chemistry goes out there, also to interpret telescopic data and sample return data. So between the IDP work and the lab work, I was asked to participate in the Stardust mission and saw that entire mission from cradle to grave, and got to extend my studies of extraterrestrial materials that land on us to extraterrestrial materials that we bring back to land on us. And then, once you do the first kind of mission like that, then you're one of the experts. And so, you're often pulled in to help with missions that follow. And so, like you said, I worked on the Hayabusa and Hayabusa 2 missions, which are JAXA missions that NASA participated in, and then the OSIRIS-REx mission. And I even had a little bit to do with the Genesis mission, which was a NASA mission that returned solar wind gases from the sun. I only played a small role in that one, but it was still a sample return, even if they were just atoms.
I've heard you give a really beautiful sort of analogy as to why these sort of missions are really important, the sample retrieval missions, is that when asteroids or meteorites land on Earth, we have a free sample. It takes very little to retrieve them and then do the testing from there. But they're not pristine. They're oftentimes contaminated, and so there needs to be a great effort into retrieving pristine samples. So it seems to me like one of the biggest goals or reasons for doing these sample retrievals is to collect those pristine samples. Can you give us a little bit of insights into that? And also the idea of free solar grains, if you don't mind.
Yeah, sure. So actually there's multiple advantages of sample return, one of which is that you have much more control over whether your samples get contaminated or not. I mean, when meteorites land on us all the time, but they land in the mud and they land in plowed fields and they land on asphalt and so on. And so they get contaminated by terrestrial materials pretty much immediately. And if you're interested in organic compounds carried by these bodies, you have a real problem because the Earth has got, there's pretty much life everywhere on Earth. And so you can contaminate the organic inventory very quickly. So if you can bring something back and control the way you bring it back so that you make sure it's not exposed to these kinds of things, then when you measure the organic compounds in the sample that they're really associated with the asteroid and the sample you brought back, that they're not just the fact that you landed in some mud and picked up some bacteria or something. Of course, you have some other advantages with sample return also, which is while asteroids provide us material in the form of meteorites and they're almost for free, they're also orphans. So when you get a meteorite, you don't know where it came from. And so you can measure lots of things of it, but I can't necessarily put everything into context because you don't know the body it came from. You don't know how big it was, what it looked like, what its history might have been in terms of collisions and where it was formed and so on. So when you go to an asteroid and you get a sample and you bring it back, then you have all this data you took while you were at the asteroid and you know what it looks like, you know what its size is. You can put your sample in the context of the overall body. And that means that when you do measure things in your laboratory, you get this extra bonus understanding because all that data isn't from an orphan. It's from something where you know its heritage.
Right. You have a provenance or a chain of command.
Exactly.
Right. Now, I think it might be beneficial to define the term organic because when people hear that term who might not live in the science world, they might be thinking either organic food or something that might be living, right? What do we mean by organic?
Exactly. Well, so I'm using it in a very broad mode that we're basically talking about being interested in the chemical compounds in the sample that contain carbon, oxygen, nitrogen, the kinds of elements that play and molecules that play a major role in life on Earth, for example. But there are plenty of organic compounds which life doesn't use. And we're interested in those as well because when the Earth first formed, objects like Bennu probably were dropping material on the Earth and providing your sort of original feedstock for getting life started. And so then you're interested in all the things that were dropped because we don't know how life got started, so we don't know which compounds are important. We know which ones are important now.
Right.
But that doesn't necessarily mean that there weren't other compounds that played real key roles early on and then life, once it got going, just abandoned. So we're interested in basically all compounds that contain carbon, oxygen, nitrogen, hydrogen, sulfur, phosphorus, some of these elements that play such an important role in biochemistry on the modern Earth.
So OSIRIS-REx, in the beginning, any mission that you're designing from scratch early on, of course you have to have a target. How did your team ultimately land on, metaphorically, Bennu as a target for your sample retrieval?
Well, it was a longish process in which we sort of winnowed down the candidates. So in order for us to go there and get a sample, you have to meet a bunch of criteria. An important one of which is, can we get there for the money?
Yeah.
And so, there are lots of interesting asteroids all through the asteroid belt, but some of them would take so long and so much money to get to that they're just not a viable candidate for a mission like this. So Bennu is conveniently located. It's in an Earth-crossing orbit, and so it requires a relatively low delta V. In other words, not too much fuel to get to. And so that put it in a subcategory of ones we could even consider. But then in particular, since we're very interested in organics, and we're also interested in very primitive objects that haven't been altered a great deal since they formed, we were particularly looking for asteroids that look like they might be carbonaceous, contain a lot of this organic stuff, and that showed evidence of consisting of materials that don't look like they've been completely reprocessed. I mean, an iron meteorite, iron asteroid would be an interesting asteroid. We're sending a mission to one now, but that isn't a good one to go to if you're interested in the early organics that were delivered to the Earth. So Bennu fell in a category that suggested that it was likely related to the carbonaceous chondrites, which are the kind of class of meteorites that fall on us all the time that are rich in carbon and contain organic compounds. And so basically by considering all of these sorts of characteristics, we narrowed it down to the point where we realized Bennu was an excellent target. We could get there, and it looked like once we got there and got a sample, it would be extremely interesting one for the kinds of questions we wanted to ask.
Now, you've been a part of many of these missions now. What's it like? I guess I should ask, first of all, were you there on launch day?
Yes, I was.
So what's it like seeing, strapped to an Atlas V rocket, going up, and you've put so much work in advance of even, getting into the atmosphere, watching that payload go up, and what's that like?
Well, it's mostly exhilarating. I mean, it's just amazing to watch. It's very visceral. There's a lot of noise and flash and all of that. And it feels wonderful to see, your many years of preceding hard work pay off. But there's a little angst too, because of course, until it's safely on its way, there's always the chance it may not be safely on its way. So it's a little nerve wracking too. But the OSIRIS-REx launch system just behaved like a champ, did everything perfectly right, and got us on our way to Bennu in perfect order.
So essentially, maybe the first point of celebration along the way. I mean, once it was approved, that's something to celebrate as well. But this is the first.
Yeah, well, that was a big celebration too. I ran up and down the halls, jumping up and down and yelling at everybody. But because it's a lot of work to get to that point, and then of course, it's even a lot more work to get the whole thing built and stacked and ready to go.
Of course.
So there's lots of places to celebrate along the way.
My favorite part of any launch, and I try to watch all of them, especially with what SpaceX is doing today with Starship, is the reaction of the engineers and the scientists in the control room when that bad boy goes off, and you see how happy and excited they are. It's just a window into human ingenuity and just love of science. So I would imagine it was something like that when you finally reached orbit.
Yep.
Now that was in 2023. How many years prior to launch did it take to get to that point?
It kind of depends on where you want to start the clock. So NASA, for these kinds of missions, NASA selects them from a series of people who send in proposals, so you compete. And so I was one of, I think, 5 people who were on an original proposal to fly an earlier version of this mission that was given good feedback, but not selected. And then later, and that was just called OSIRIS. And then later we reproposed with OSIRIS-REx. And many of the people were then new at that point, and we'd modified and improved the mission. And then we did get selected. And so, from first inception to final return of the sample is, measured in decades better than years. So sample return missions, most missions are long because they take a long time to create, a long time to build, a long time to fly. Sample return missions are often even longer because once you get there, you get your sample. Now you have to come back.
Right.
And so that adds an extra difficulty for the mission because your hardware has to be capable of doing a multitude of different kinds of actions, and then it has to live long enough to make it all the way back to the Earth. So it doesn't do any good to capture the sample and then fail to bring it back. So.
Right. That's what I love about these missions is, there are so many points of possible failure, and you have to overcome every single one of them in order to retrieve that sample. And this mission was not without some issues, which we'll get to certainly. But Bennu, 63 million miles away, you begin to approach it. You begin to start scanning for landing sites, and you ultimately landed on a site known as Nightingale. But before you picked that site, you guys were thrown a curveball because you realized that it was not as smooth as you had expected.
Yeah, right. So someone had failed to tell Bennu how it was supposed to be for us.
Right.
So if you looked at early artist conceptions of the whole sampling system, you'd see this animation of the spacecraft coming down, and a sampling a fixture would be pressed down against this sort of rounded beach of looking sand, nice and smooth, and there'd be a little puff of dust, and then it would back up with our sample. But when we got there, we found out that the surface was just utterly covered from one end to the other with boulders of all sizes up to houses. And so there were no easy, smooth, soft-looking places that were obvious to land. And we have a constraint on our sampler. The way it worked is we couldn't really grab and ingest stuff bigger than a couple centimeters in size. And so we needed a place that was predominantly covered by small rocks and dust, not boulders. And so the initial idea was the hope that a good fraction of the surface would be available for us to consider sampling at. Well, instead, we ended up having to do a great deal of work to more or less search every square meter of the asteroid, looking for places where we thought we had a good chance of succeeding in capturing sample.
And whether it was intended or not, I'm sure it was intended, but that resulted in some beautiful imagery of this beautiful asteroid that's got this sort of egg-like shape. You'd say
it's well here. This is its shape.
Oh, well, there you go.
So this is a 3D model one of my brothers and I printed, and so you can see some of the boulders that are the sizes of houses. This whole thing, its dimensions is about a half a kilometer.
Yep.
So it's big, but not that big compared to many other asteroids. And it's kind of an oblate spheroid. You can see it's more or less round, but it's got this sort of ridge around the middle that bulges out a bit. And so we had designed the mission. We knew that it was already pretty much in an orientation like this, rotating every 4 hours, and that almost the entire surface would be in the sun at one point or another during the rotation, which is, we're just really lucky the way the axis was oriented. And so the plan was to take pictures at multiple scales of the whole asteroid. So that gave us and we also had a laser altimeter on it board. So that let us make a very precise shape model of the whole asteroid. So we know where the rocks are and the boulders. And then we had to go through all of those images and all that data, trying to find a good place where all these big boulders aren't in the way. And there was a surface that was smooth enough and dominated by small enough material that we could actually have a good chance of going down and getting the sample successfully without risking the spacecraft's safety.
Now that bulge at the equator there, is that is that a byproduct of the way it was formed, or is that something more due to gravitational forces like we see on Earth?
Yeah, it's a couple things. So first of all, we know this is a rubble pile asteroid. So this is not a big rock with some little rocks on it. It's probably just a jumble of small rocks all the way down. And it is probably the reaccumulation of material that was blown off a much bigger parent body in the old ancient days of the solar system. There was probably a much larger parent body, probably 20 to 50 times bigger than this, that was broken up into pieces, and some of those pieces reaccumulated to make Bennu. And so since it's made up of just a jumble of rocks, it doesn't have a great deal of rigidity. It doesn't have a lot of internal strength. Mm-hmm. And so most of these rocks and the gravity on the surface of this body is really almost negligible.
Right.
If you were on the equator and you did a nice vigorous push-up, you'd probably just throw yourself right off the asteroid.
Right.
So what that means is that most of these rocks are not nailed down very well, and so they're easily made mobile. And since this thing is rotating pretty fast, every 4 hours it goes all the way around. There's a tendency for material that is disturbed to want to move towards the equator, like on if you're on a merry-go-round, right? There's that.
Right.
It's trying to throw you off the merry-go-round. So material probably over time migrates this way. And so we've built up this belt here in the middle, which is probably consists of a large amount of material that has moved down and up from the poles to this position. So it's a combination of rapid rotation and weak gravity that's probably defined most of this shape.
Right, and that weak gravity in rubble pile eventually was a bit of an issue when you collected your sample. But before we get to that, and before there was touchdown, correct me if I'm wrong, OSIRIS-REx, it holds a couple of interesting records and facts, but one of them being that it is the closest orbiting man-made object to a celestial body at points, right between 1 and 2 kilometers.
Yeah, and we know that because it's in the Guinness Book of World Records, so it must be
Wonderful.
true.
Yeah.
But yeah, since its gravity is so small, in order to get in a stable orbit about it, we had to get really quite close. And so that's one of the main reasons we hold that record, is that an orbit wouldn't even be possible if we were very far away, because the gravity wouldn't be strong enough to hold us with the asteroid. So it required, the mission, these missions only work because you have a large number of people who really know their stuff in a lot of different areas. And
Right.
our navigators did a super job of getting us there, getting us around the neighborhood while we were there, and then getting us back. And all these maneuvers required a high degree of precision to pull off.
Can you speak to the technical nature of the actual? I'm curious about the propulsion system. When you're adjusting, going closer and back and forth, are these cold gas thrusters, or are you?
Yeah, so the delta, the velocity changes required are really incredibly small because you're not in much of a gravity field. So you just use small thrusters to give yourself little pushes that just modify your orbit, and then you let time get you where you want to be.
Right.
And so there were a lot of propulsive events, but they're all very subtle things.
Right. So relying heavily on
Nothing like the
Newtonian
rocket
physics.
breaking off from the pad.
Right. Exactly. So bring us back then to the day of touchdown. So the way that this was going to work, OSIRIS-REx has the TAGSAM, the touch and go specimen acquisition mechanism. It's kind of like a punch hole, or a hole punch, depending on what part of the continent you're on. And tell us about that. How did that mechanism work? And
Well, so the way it worked is we had a long arm that hung down below the spacecraft, and that was the only part that really touched the asteroid. And at the bottom of it was a disc about this big around, and the disc had within it a round filter, kind of about the size of an old-fashioned air filter on a V8 engine. And the idea was, as this pad came in contact with the ground, we opened up a valve that let pure N2 gas, nitrogen, flow down and out of some nozzles, and they would stir up the material underneath and mobilize it so it's flying around. And some of this material would go up and hit a deflector plate that would then shoot it sideways through a kind of mylar flap, like a cat door kind of, that went all the way around this. And then material would get pinned up against this filter area and captured. And then the idea was that when we were done and the gas stopped flowing, these flaps would fold down and all the material would be captured in this ring.
Interesting.
And
this just occurred to me, and I am no space engineer at all, but would something like a centrifuge inside a collection mechanism help to concentrate the material on the outside so you could collect more?
We used the gas flow to do that. So the gas flow was supposed to go up and out through the filter. That's why it was a filter instead of just a metal plate or something. If it had been a metal plate, we would have pushed gas in there, and then the back pressure of that gas would have pushed back on us, and it would have kept other material from going in. So we wanted the gas to flow down and then up and out to collect stuff. And anyone who watches the actual footage of us doing this realized that a lot of this gas didn't just push stuff up and in, but also push stuff out and out, all over the place. But fortunately, the system worked well enough to get us more than twice as much material as we needed to get to meet all our science requirements. So it did everything we needed it to.
Right. You were shooting for about 60 grams and ended up with about 121, 22 grams in total. Mm-hmm. Now, what I found fascinating in following this is that when the touchdown happened, and I don't think that you guys expected that 6 tons approximately of material was ejected when this happened, and that was due to the loose rubble nature of the asteroid. I heard somebody describe it as being almost like a foam, that if you were to step on the surface of Bennu, you might actually sink a considerable amount into it.
Well, if you had velocity to push you in, but the
Right.
gravity itself wouldn't pull you in. But
Right.
so I should correct something I said earlier, that if you're at the equator and you did a push up, it would throw you off. That's only if you could actually do your push up against the surface. But as what might happen is you might push down with your arms and find out you just pushed your arms
Right.
into,
Right.
into the surface, and you're still there. Yeah. So I guess I wasn't surprised that stuff went flying everywhere. You can do a simple calculation of energy, how much energy is contained within the gas bottle under pressure, and how little gravity there is holding everything together, and then take some estimates of the mass of the rocks and do a calculation, and you quickly find out you have enough energy there to mobilize massive amounts of material. So I wasn't sure exactly how it was going to look, but I wasn't the least bit surprised when things went flying everywhere.
Right. Right.
And as long as that stuff flies away and doesn't harm the spacecraft, and that we collect the sample we want. And since I'm largely in this for the sample, I was a happy guy. But in addition, the fact that you launch stuff actually could be used to do other science. You could see where this stuff, went, and it gave us a good indication of how weak the surface really is. So.
No, actually, that does actually answer one of the questions that I had, which would have been, were there any precautions in advance to prevent OSIRIS-REx from altering the trajectory of Bennu?
Yeah, so the same energy calculation tells you that the actual push was absolutely negligible. Okay,
right.
We didn't affect its orbit in any particular way at all. The forces involved with our sampling are just trivial compared to the mass of the overall asteroid, and so Bennu's trajectory is actually being modified more by the pressure of sunlight on its surface than by the OSIRIS-REx spacecraft encountering it.
Right.
And in fact, that's one of the things we measured, is that that the Bennu asteroid its orbit is in fact evolving just because of pressure from solar radiation and the effect it has on the surface.
Now, the reason why I was going to ask that question is because there was a time when Bennu was thought to maybe be a impact threat on Earth, and so the trajectory might be an important thing. Is it still considered a threat?
Oh yeah, it's on a trajectory. It's an Earth-crossing asteroid, and so it crosses our orbit every few years, and there is actually a period starting in about the 2130s, I think, where there are small chances that it could hit the Earth, and this goes on for a number of decades before its orbit evolves on to where it's not really a problem anymore. It's never a big threat. I think the highest odds for any of these is like 1 in 10,000 or something. But this is also one of the reasons we picked Bennu to go to, is because since it was on the hazards list, it made good sense to go there and characterize this object so we understand it. And our effort, gave us a much better understanding of the orbit, so we can be do a much better job of trying to understand whether it ever might hit us. And then also, if it turns out that we think it might, we'll really understand this body, so we'll know much more precisely what we should do about that. So it's not a hazard now. It won't be a hazard for us. But our grandchildren might be paying attention just to make sure it stays that way.
So let's fast forward then and sort of look back at the return. Right, this is OSIRIS-REx, I believe, was the second fastest man-made object to enter the atmosphere at 43,000 kilometers an hour, which is an incredible amount of energy that needs to be dissipated with its ablative shield and that sort of thing. And you were there in Utah, waiting for it to make impact, a gentle impact in the desert of Utah, about 500, 600 square kilometer target. And you were one of 3 people who were there to say hello, to greet back.
Well, there was more than 3. I mean, we had a couple of helicopter loads of people. There's some pictures where there's 3 of us there, the 3 of us who were some of the first to approach it and to check out the state of the SRC, the sample return capsule, to make sure it was in good shape. Because if it had come back and was damaged in any way, then we would want to follow procedures that made sure that we did everything we could to maintain the pristine nature of the sample. But the capsule actually touched down pretty much perfectly. I mean, as you've seen the pictures, it's like actually balanced on its nose cone, which was surprised the heck out of me when I saw that.
You can see in the sand the way it rolled like a top.
Yeah, well, so there's a couple pictures. You're probably thinking of the Stardust one, maybe, but when Stardust came down, it was in a crosswind in the middle of the night in a snowstorm, and it hit moving sideways.
Yes, that's right.
And so it hit and it bounced and flipped, and it hit and bounced and flipped, and it hit and then eventually ended up on its edge and rolled for a while like a quarter on a desk, and then it finally laid down on its side.
Right.
And it did go in a circle at that point. You can see in the mud the circle as it went around in a.
That's the image I was thinking of.
Yeah. Right. So OSIRIS-REx came down during the day, which made it a lot easier. There was no storm, which made it a lot easier, and it came down on its parachute almost perfectly vertically. So it came down and it hit on its nose cone and it bounced up and landed on its side and then just rolled back onto its nose cone. So it rolled back into the original divot. And so it had a little cup after it hit, and when it impacted, it crushed enough soil down to make a divot, and it rolled back into that and balanced. And so when we first got there, I thought like, okay, who's been messing with the capsule and tipped it up on its nose? Because that's not a stable way for it to be. But when you went and looked very closely, you could see the divot where it landed on its side and then just tipped right back in. So it was a very elegant landing. If I had been holding a card up, I would have given it at least a 9.9. And that also meant that the capsule was not put under any particularly additional stresses associated with breaking any seals or causing anything to have the potential leak. So this meant our sample was inside, nice and safe, completely uncontaminated by any of the local soil or vegetation or anything else. And so it was a really excellent touchdown.
I love the video of the sample canister closing up and the whole return capsule getting ready, to leave Bennu, and I can't help but think, oh man, what a crazy gasket that must be. The plumbing in your kitchen, oftentimes the gaskets, they just go, or you can't get it to work properly. But what incredible engineering is involved.
Yeah, I mean, a lot of testing there, and we did have some advantages that many aspects of the capsule for Stardust and for OSIRIS-REx were very similar. So we had a lot of testing from the Stardust capsule that helped us with the OSIRIS-REx one. But the actual details of the sampling mechanism and how it had to be contained and so on were a bit different. So on Stardust, we had no camera that could take pictures of the whole thing sealing up. So we weren't really, we had various sensors that said it all worked fine, but there was still a little bit of residual anxiety in the back of our head that when we entered the atmosphere, was everything really the way it was, tightened up the way it was supposed to be. In the case of OSIRIS-REx, it was lovely because we could see the sample canister collector being put into its holder, seeing all the detents clip onto place, see the arm pulling out, and then watch the whole clamshell close up and button up tight. So that was great, gave us a lot of extra confidence that everything was ready to come back. We did also see some, when we were clipping the collector in place, see some particles drifting out. So we knew we were losing a little bit of sample. So that's one of the reasons we decided to close up more quickly than we might have otherwise, is because we didn't want any of the precious stuff we'd grabbed to get away.
Of course. So which of the two events, in your opinion, launch or reentry is the more stressful one, or an enjoyable stress? Which of those is more memorable to you, I guess?
So since I'm in this for the sample, I guess getting it back in my hands, so to speak, is maybe the most visceral one. I mean, the launch is impressive because of the sheer power of it. I mean, it's impressive to be miles from the launch pad and feel your whole body vibrating because of all this energy that's being expended. But I've had a feeling just a couple times in my life that's a little hard to describe, but one of those times was when the Stardust capsule came back, and you just suddenly realize that, amazingly enough, you're kind of participating in a bit of history. I mean, Stardust capsule was, I believe, the first thing made by humanity to leave the Earth-Moon system and come back, and here I am on the team picking it up,
standing right in front of it
to get it back. And so most of the time you're busy working. You've got a lot of things to do. You've been practicing them for months, and you're getting on with the job. But every now and then you get a little bit of time to be, retrospective, like when you're in the helicopter flight heading back to the main site, where you get a moment to reflect, and in which case you do kind of have a interesting gee wow kind of moment.
I could only imagine.
And so I had the same feeling on OSIRIS-REx. Maybe it was a little less intense because I'd been through this before, but it was still a very real, very visceral thing. I mean, you look at the capsule and you just think, the places you've been,
right? Yes,
the things you've seen.
Amazing. And I mean, a little bit of delayed gratification because you could not open that capsule right away. It took months for you guys to
we had to be really patient, but we practiced that by being patient for the whole mission, right? So as a sample return person who's interested in the sample, you have to be patient because you've got to get through all these things. You mentioned how there's these various stress points along the way. Well, the sample scientist gets to enjoy all of those because anything can go wrong up to the very end. If you're someone who's taking images of the asteroid, at some point you've got all your images, and if the failure happens after that, you still have everything that you needed to do your part of the effort. But for the sample scientists, everything needed to work right up to the end. So it was a little frustrating waiting to get everything out, but on the other hand, we'd already done a lot of waiting, and also we knew the sample was there. We knew we were going to get it. It was just a matter of time. So we just had to be patient for a little longer.
Couple of more sleeps, right? Now, before you could get into it, you guys ran into an issue with some screws that were essentially stripped because of the fact that you collected so much material. Can you tell how you guys got around that problem?
Yeah. So, it wasn't because we had too much material. It was because of a self-imposed restriction we had on the tools that were allowed in the glove box. So the sample went into a special glove box that was purged with nitrogen so we could keep it pure while we were disassembling everything. And one of the ways to limit the kinds of contamination you could have in the sample is to restrict the number of things and the kinds of things that could be in the glove box. I mean, you can't get contaminated by something that isn't allowed to be there. And so we had made a conscious decision that we would only allow a certain list of materials to be inside the glove box. And one of the things we didn't want to have is 18 different kinds of steel and aluminum in there, all of which could potentially contaminate us. So we made special tools out of a limited set of metals for things like the screwdrivers that remove the screws. And so normally when you use a screwdriver in your garage, you're using something that's got is made of steel, which is designed to be very, very hard and to be able to handle any screw. And so if you have problems with screws, it's usually because you stripped the screw head, not because you wrecked the screwdriver.
Right, yes.
But we made screwdrivers out of a limited list of metals and discovered that some of the screws had gotten tight enough, either from during their installation or just from flight over time. Metals do vacuum weld, for example, with each other, that the screws were set in there hard enough that when we tried to use the screwdrivers we specially had built, that the screwdrivers themselves were the things that were starting to bend, not the screws. And in either event, we wouldn't want either one to be deformed because that would have the potential of getting little bits of that metal out as a contaminant. Right. So we got most of the screws off. We got down to the last two and found out that every screwdriver we were trying to use was starting to deform. And so we thought we'd got to stop. Otherwise, we could contaminate the sample with screwdriver. And so that required we back up and think about our materials again, find another material that we decided was acceptable to be introduced into the glove box and get screwdrivers made out of.
I see.
That material, that harder material. And then once we had that, then of course we needed to practice it on engineering models to make sure it would all work. We're not going to go test out a new idea on the actual sample container. And then once all that testing was successfully done, then we could go back and do it. So this took some time and the development of some replacement tools, but it worked.
So what sort of, because I'm very familiar with decontamination procedures for a tissue culture hood, as an example. If you have to, or any material that you're introducing into this nitrogen purged hood, what are the decontamination protocols? I mean, are you autoclaving them to make sure nothing alive gets in?
Yeah, well, there's a whole series of cleaning steps that and involve, and depending on the material, you can bake material, but you don't
Right.
want to bake something that itself would combust or something.
Right.
You can use ultra pure solvents, special kinds of cleaning cloths, and so on to minimize and eliminate things that are carried in that you never intended to carry in, dust on things, right? You don't want surfaces to have any kind of dust on them. But nothing's perfect. And so you also hedge your bets by maintaining a large archive. So before we even launched, we archived all samples of all the materials that could potentially ultimately get into contact with the sample. So we archive bits of the aluminum from which the sample canister was made. We archived bits of the heat shield and the back shell, so we would recognize if flakes of that got into anything, and so on. And so all of these potential contaminants are archived in their own curational area. And so you can then go back and study those against the sample you got to just make sure that you don't find matches. So, for example, one of my many jobs for OSIRIS-REx is to lead a team that's analyzing the sample return capsule to see what the material in the capsule looks like after flight, so we can know what it would look like if it accidentally got into the sample somehow.
Right, so you can remove it from any background noise of any
You're
signal.
right. So if you say like, oh, hey, during ablation, some materials actually did get into the SRC. If we'd had that seal had broken, for example.
Right.
What do those look like, so that if we find those in the sample, we don't go off and shout to everybody that Bennu contains ablated heat shield material.
Right. Yeah.
We would know that that's a contaminant and to be very cautious about that. And so, so you tackle this from both directions. You do everything you can to absolutely minimize contamination. And OSIRIS-REx spent a lot of effort on this, and the indications are we did a really good job of it. But then you also, like I say, you hedge your bets to make sure that you're not assuming things are going to be perfect, but you're checking that they really work.
Right.
And you have ways to check. And then if you find out that there are a few issues where maybe it didn't work, or you're not sure if it worked the way you expected, that you have a way of assessing that and accounting for that, so that you don't end up reporting things that aren't true.
So how close to zero did you guys get?
Well, to my, it kind of depends on which part of the sample you're talking about. We do see a few things. So we had some of the sample got out of the actual collector and it was on the avionics deck around that. And there are a few things here and there that look like they're little bits of the interior of the SRC. And so those are probably contaminants. But inside the canister, where the sample was originally all supposed to end up, it looks like we did a really good job. I'm not aware of any difficulty people are having studying the samples of being utterly confused about whether something they're looking at is Bennu or not. So
that's great news.
I mean, there are a few things where no one's reported on them because we're still trying to make sure that they really are. But when we're being sufficiently cautious, that we've seen a few things that were strange enough that we worried about it, whether it was contamination, and then did the work and said, like, no, this is really Bennu. This is amazing.
So, now, before we get into those results, you ended up with 121 grams. You were shooting for 60. Now, that in your world is a huge score. Now, for people who might not be so well versed in space science and collection, why not? Is it impossible to collect something more like a kilo or 2 kilos or 10 kilos? What are the limitations? Why are there limitations?
Well, so first of all, the more mass you want to bring back, the more what your sample return capsule has gone away, the bigger everything has to be. And for a spacecraft mission, big is in general bad. You increase the size of something by 10%, you probably double its mass, and now you need 4 times as much fuel, and on and on and on. So you can price yourself right out of existence by trying to go bigger. But the size of the sample you need depends a lot on the nature of the sample. So if I were going to sample a metal-rich asteroid, I'd want to bring back a big mass, because the indications would probably be that the sample is present on large scales, that the lumps of metal are big, and you want to get a representative chunk of metal. In the case of Bennu, we knew it was probably closest to a carbonaceous chondrite. These tend to be fine-grained materials. The size of the components are quite small, and so if you want a representative sample, you don't need as much material. So how much you need does depend on the nature of your sample. And we sample scientists have gotten very good at dealing with extremely small samples. I mean, the Stardust mission brought back only a fraction of a milligram of material, which sounds like almost nothing. But we have the technology. Once you have the sample back on Earth, you're not limited by the instruments the spacecraft can fly. You're only limited by the facilities on the Earth. So, for the Stardust samples and for the Bennu samples, we're doing analyses at facilities that are not just bigger than the spacecraft, they're bigger than the launch pad the spacecraft left from. And so this allows us to look at very, very small things. And in the case of the Stardust samples and the OSIRIS-REx samples to some degree, the fine-grained nature of the material means that a lot is happening down even at the micron size scale, millionth of a meter.
Yeah.
So small you can't see it with your eye. And so I've been the co-author on a number of papers now and have at least one more being reviewed right now. And the vast majority of those papers are all about what we learned from samples that are very small. And in fact, the paper that's being reviewed now, the whole thing is based on a couple of particles that are about the 20th of the width of one of the hairs on your head. So all other things being equal, more samples better, because you have a better chance of sampling variety or getting a more overall representative sample. But in the case of the Bennu sample, the 60 grams was not selected kind of out of the air. We spent a lot of time thinking about how much would we need to do this kind of analysis, how much would we need to do this kind of analysis, how representative do we expect the sample to be, and that's how we came up with the 60 gram number. And if I was going to a different asteroid, I would want the team to do the whole analysis again, because the number may very well be different.
Right. And despite the fact that you collected, I don't want to say only 120 grams, but you are saving up to 70% of it for future generations to study.
Yeah. So our calculation actually was to find out how much material do we need to do the science that we have promised to do with the mission.
Right.
And the answer for that was 15 grams. But we also, for sample return missions, you don't bring the sample back and give it all entirely to the sample analysis team, and then they make some measurements and say, well, that was interesting, and then they throw everything away. No, you bring it back, you let them look at a portion of it so that they can answer the questions they're supposed to answer, understand what the sample is. But most of the sample is kept in a curation facility where it's maintained pristine, and then it's available for future generations to study. I mean, this is the way it's worked for all of NASA's sample return missions. I mean, people are still studying moon rocks from Apollo because they've been curated and kept very pristine after they came back, and people can request those to continue to do analysis. And so since we were only allowed to have 25% of the sample and we needed 15, that meant we needed to bring back 60 so that future generations have that extra material to work with. And so there are people who will continue to be learning about Bennu who, from those samples, who aren't even born yet.
Right. And that's presumably in some part because they'll have technologies and techniques that have not even been thought of.
Exactly. So, our analyses of our sample are better than we would have anticipated when we launched, because technology marched on while we were in flight. Okay. And so all our techniques improved over that time, and they'll continue to improve. And so future generations may be able to make measurements we're not capable of yet. If someone in the future invents psychic infrared spectroscopy, then they can request some sample and do psychic infrared spectroscopy on it and learn new things. So we'll continue to learn new things just using the techniques we already have, because we'll be asking more and more sophisticated questions and have a better idea what we're hunting for and so on. But in addition, people will make measurements that I can't even conceive of right now. And so this is one of a number of real powers with sample return, is that the samples just keep on giving. And so the science is sort of semi-endless that you can get. So totally get your money's worth because long after the mission stops being an official mission, you continue to get the benefits from it.
So let's turn our attention to some of those results that you published recently that got a lot of worldwide headlines, and the two biggest points are 14 of the 20 terrestrial amino acids were identified in the samples, as well as all the 5 nucleobases, the basic building blocks of life that, as I mentioned in the onset, molecular biologists like me are just fascinated with and work with on a daily basis. So, can you give us a rundown as to the importance of those results and maybe what that tells us about potential of life being elsewhere in the universe?
Yeah, sure. So, I mean, obviously, the focus with people has been on the detection of amino acids that are used by living systems on the Earth now, because that seems to be pretty obviously potentially related to how life got here. But actually, of equal interest in many respects is the fact that we also found a lot of other amino acids that aren't used by life. And so, and in fact, a whole host of organic compounds, tens of thousands of them that are not necessarily used by life now. So this tells you that the processes that led up to making the Bennu sample that we grabbed, and these may have been processes that occurred in many different locations over large spans of time, supported a very rich organic chemistry that made all kinds of things. Okay. And this chemistry is not biological chemistry. I mean, biological chemistry on the Earth is very productive, but it doesn't make everything. It makes specific things it can use. Right. And so what we're seeing is a much richer chemistry, a much richer population of things, which tells us that we were getting stuff from abiotic processes that were making everything from soup to nuts, so to speak. But not biologically speaking, and that this material was there waiting to be delivered to the surface of a planet. So this kind of tells you that the universe is apparently hardwired to make complex organic populations of materials. And so when you make a planet, this stuff is probably delivered, and then it's available to get going. And since we don't really understand how life got started, it's hard to assess the importance of any given molecule or set of molecules. But if you have a little bit of everything, then who's to complain, right? And then if you get life going, life starts. Once you get evolution going, life figures out a way to do everything better, and it decides what's the best stuff to use and what it doesn't care about so much. And then you winnow down the population to a more discrete set of things that we now see in modern life. So, so we see the 14 of the amino acids that's used by life, but we see a lot of other amino acids. And who's to say those amino acids weren't important for getting life started?
Sure.
But later on, we found a better way. It's the same thing with the nucleobases. We see plenty of nitrogen heterocycles that could have been nucleobases potentially, but for whatever reason weren't selected or didn't work. And so, I think one of the most profound things about this, and this is something I've known for a long time based on other things as well, that the universe is hardwired to make complex organics. It just does it. In the other half of my life, I work in a laboratory, which is on the other side of the door over here, where we can simulate environments in outer space, in particular very cold ones like the surface of Pluto, comets, the interstellar dense molecular clouds, where we process with radiation mixed molecular ices of the type we have identified in space using telescopes. And that radiation processing of ices makes these compounds. I can make amino acids in my lab. I can make nucleobases. I can make sugars. I can make all these compounds that life uses. And these are using processes that must happen every time you make a planetary system. So I think you make planets, this stuff will come in most cases. And so insofar as the delivery of this kind of material plays a role in getting life started, I think it really raises the odds that life is not all that rare out there. I mean, I don't know how common it is, but it can't be uncommon. It can't be so rare that you'll never find it anywhere else.
And the interesting thing about these amino acids, and you sort of alluded to evolution and biology finding the best way forward, is that these amino acids were racemic, and meaning that about 50-50 in terms of populations of D version and L version. For those that are not familiar, molecules come in two mirrored forms. And on planet Earth, biology has sort of leaned towards the left-handed version
Yeah,
of these
well, leaned
amino
hard.
acids. Yeah.
So,
Yeah, very hard.
so
Yeah.
for anyone who doesn't understand the whole idea of chirality, there are some classes of molecules that can have the same chemical formula but have different mirror image structures. And the best example I can give easily is my hands. So my hands have the same chemical structure: one palm, one thumb, four fingers. They both have that chemical structure. And they look similar, but they're not the same, because when you go like this, you find out the thumb is sticking out on the wrong side. So that's why I have a left hand and a right hand. And amino acids have this same property, that they can have a handedness. They can be in the D or the L form, right or left-handed. And for whatever reason, and lots of people love to argue about this, particularly over beers, life chose to use left-handed amino acids, and we don't know why that is. It could have been a luck of the draw. I mean, it could have just been, that some puddle got started with left-handed first, and then it's the winner, and we're done. Or it could have been that there was some subtle thing driving us in one direction or the other. And there are processes that can do that, although you can argue about whether they're strong enough or would have happened in the right circumstances to do this. But it's possible that it's just a flip of the coin, in which case, we could run into aliens that use amino acids like us, but they use the other handedness of amino acids, which might be convenient, because then we can't eat each other. So we can be friends, but not cook each other.
Right. So the point being is that the amino acids on Bennu came in about 1-to-1 ratio of the left and the right.
And so when I told you I can make amino acids in the lab back there, but when I do that, I make racemic mixtures. I make equal fractions of each. And that's because most abiotic chemistry doesn't care which kind it makes. And so you get half and half. And so one of the big questions for the Bennu samples is, well, if we go there, is it going to be 50-50, or is there going to be, will we favor one of the handedness? Because it would have been fascinating to find out that the amino acids on Bennu were predominantly, or at least even slightly more rich in the left-handed amino acids, because then you could ask, well, maybe the left-handed amino acid bias on the Earth got started because the stuff that was delivered already had that bias, and therefore this bias was established in space, not on Earth.
That would have been a fascinating result, huh?
Yeah. So, but so far, all the measurements show equal mixtures, which tells you, it tells you a bunch of things. It tells you that the amino acids we're looking at are not contamination, because if they were, they would be biased towards left-handed, because Earth's contaminants would be left-handed.
Right. So
it tells us the stuff we're looking at is from Bennu. It tells us that the material is abiotic. It wasn't made by life, even on Bennu. And so it was made by some abiotic process, or probably processes, during the history of the parent body. And then it's been now sitting around waiting for us to show up and grab it and measure it. So that was a fascinating result. I don't know what my expectations were, but there were some reason to believe, from at least measurements of some meteorites, that we might find left-handed excesses. So it was a possibility. And so I think maybe there were some people on the team who kind of were surprised that it was so perfectly racemic, because like I say, there has been some meteorite data that suggests maybe under some cases there have been left-handed excesses. So now we have to go visit that meteorite data, because I don't think you can explain the left-handed excesses in meteorites solely by contamination, or at least not simple contamination. So there's still an option that maybe Bennu is racemic, but other asteroids did something a little different. We still have questions, lots of questions. But certainly the amino acids we've measured so far are completely compatible with abiotic synthesis on or before the asteroid. And tell us that the universe can make amino acids for us, but it isn't at least necessarily going to tell us which one to use.
So how have these results, if I may ask, changed or affected your outlook on that question of whether or not there might be life out there?
Oh, well, I've thought for a long time that life is probably moderately common out there. I mean, so I've been doing this lab work for the better part of 40 years now. And over all that time, we've demonstrated that, you pick any class of organic compound, modestly simple one, not DNA, but nucleobases, sugars, amphiphiles, quinones, you know, name your compound. I can make it in the lab, no problem. And you expect these things to be made in space all the time. So, like I say, if you make a new planetary system anywhere in the universe, there's an excellent chance that a very complex mixture of organic compounds is going to be deposited on the surface. So, insofar as that's a critical step to getting life going, I think you've got excellent chances of getting a start. Now, whether all the other conditions necessary to get life are present on a planet is another question. I mean, we don't totally know, since we don't know how life got started, we don't really know what the critical parameters are. But if you think of life as being an incredibly complex Lego castle, I can tell you that Legos land on planets all the time.
That's a wonderful way to put it.
To make a castle, that's another issue, and how hard that is to do is another issue. But certainly there are aspects of it that seem like a slam dunk to me. And so at least at that level, I would not be even slightly surprised if life is quite common in the universe. Now, most of it is likely not to be intelligent. A lot of it may look like pond scum. I mean, a lot of these planets may have life, but Saturday night isn't any more interesting than Friday night. But it may be quite common. Like I say, I really do think the universe, just because of the nature of the physical laws of physics and chemistry, kind of hardwired in the environments that make stars and planets to make complex organic compounds. They're out there and pretty much everywhere.
What would you say to somebody, and I've dealt with this, and scientists who deal with either the really big or the really small, sort of two ends of the spectrum, which are very intangible to people who are not scientists. And so people who are not scientists, let's just say lay people, oftentimes have a problem with sort of, let's say on the small end, you're working with molecules and enzyme and DNA, and you can't see these things yet. We know what's happening from the data we collect, and we interpolate and extrapolate and come up with theories and hypotheses. But people just have a tough time sometimes saying, well, you can't know that for sure because I can't see the molecule, or you can't jump to that conclusion because you're using a radio telescope to deduce the shape of a planet that I can't lay my eyes on. Do you know what I'm trying to get across?
So, I mean, this is the seeing is believing aspect,
right?
As I said.
Yes.
So, but the fact of the matter is, you accept things all day, every day that you can't see, but you know from vast experience or so, and that's because we don't just. I mean, we do have senses. We have our ears and our eyes and things, but the way we process that information is with our brain. Okay. Right. And we can use our brains to understand the universe around us using a whole host of tools and not just our physical senses. So, scientists have, spend their lives learning a giant toolbox of skills of ways to poke and prod the universe. And these tools are subjected to just a huge numbers of tests to validate them, to make sure they really work and that they fit together. And then once you have a tool that works, then you can use that to learn new things. And sometimes the most interesting things you learn is that when a tool maybe starts to break down, then you know that there's something more sophisticated going on than you imagined. I mean, for a long time, we got along with Newton's laws, but then eventually we found out Newton's laws as a tool broke down. And that's when we got into relativity.
It's a perfect example. And then it starts to break down even further when you have the quantum that doesn't.
And so some of the most exciting times in science are, in fact, when the way you think should work don't quite work, because that's telling you there's some new science to find. If every time you measure something, you get exactly what you expect, then you're validating your model, but you're not necessarily expanding that model or learning anything new. I know a lot of people feel like when scientists work on stuff that their number one goal is to get data, to get facts. Mm-hmm. But facts are not, I mean, they're important, but they're not what you're really trying to do. You're really trying to build up models of how the universe works, and the facts tell you whether your model is right or wrong. And and facts, strangely enough, can sort of change. Someone can measure the mass of the electron and give you a number to 8 significant digits, and they've done an excellent job of that. But that fact will change because at some point someone will be able to measure it to 12 significant digits, and the number will be a little different. Okay, so it's not incompatible with the old measurement, but it's a new fact, right? And you have to make sure that fact is compatible with the models. And so, just measuring a bunch of facts is not it. I mean, there's a sort of the movie version of a scientist where they're sitting around a lab coat holding a clipboard, and you get this impression that they spend their day sitting around in their office, knowing stuff. It's not how I spend my days. I spend most of my days slightly perplexed, trying to figure out how does this work? What's going on here, and what experiment or test do I need to carry out to help sort this out? Okay. And so I spend most of my life at the front of research, slightly befuddled, while I try to deal with the things I don't understand yet. The things I do understand are in my toolbox. I can use those to help me understand what's going on. But in terms of actual new, fresh research, you need to be pushing this envelope.
Right. And even for everybody, including those with the sort of skepticism I outlined, their lives depend on it every single day when it comes to certain medicines or.
Well, I mean, they use the GPS on their phone to navigate all the time, and the GPS works because we understand the principles of general relativity, and they can't see any of that with their senses, but it works, and it totally fits with all the models, and so it's an application that they use every day probably, but they can't see it. So they, everybody believes a lot of stuff that they couldn't prove themselves if they had to, based on their senses.
Now, back to OSIRIS for a second. And the beautiful thing about your mission is that it's not over. OSIRIS-REx is now Osiris-Apex, and the spacecraft is moving towards a second asteroid, Apophis. Can you tell us a little bit about the second half of this mission?
A little bit. I'm not deeply involved with that, since I was the sample guy and the samples are on the ground and my activities moved elsewhere, but I can tell you a few things. So after we got the sample, we headed the spacecraft back to Earth, and we now needed to deliver the capsule, but we didn't want the whole spacecraft to crash into the Earth. So what we did is we aimed the spacecraft at just the right position on the Earth's limb so that we could kick the sample return capsule loose and send it towards the Earth. And then the spacecraft itself was diverted so it wouldn't crash into the Earth. And we used the Earth's gravity to give us a gravity assist to boost us into, or to push us into a new orbit that'll take us to Apophis. And so while the sample return capsule was coming down in Utah and I was rushing out to greet it, the spacecraft itself was passing the Earth and heading on to a new phase. Now, in that new phase, it doesn't have a sample return capsule anymore, so we can't go to another asteroid, get another sample, and bring it back. But we can visit another asteroid and use the onboard instruments to study it. So we can use cameras and our infrared spectrometers and all these other instruments to take data from a whole new asteroid. And so we can learn something about another object that wasn't on our original requirements list. So this is all, kind of bonus science. We didn't have to launch a whole new mission to get to Apophis. We're able to take a slightly used spacecraft and do the task. And so it's a great way to get more bang for our buck. And so the spacecraft's on its way to Apophis. Apophis is a different kind of asteroid. It's, instead of being a very dark, low albedo object like a carbonaceous chondrite, it's a much brighter object. So it's probably more akin to the kinds of meteorites we call ordinary chondrites. So it'll have considerably less organic stuff in it, largely be made of rock. And it's also a funny shape. It's very elongated. And so it's possible that elongation has come about because of tidal stresses from passes of the asteroid by the Earth. And so people want to look into that. So there'll be a lot of interest in the surface of this body and its overall shape. And then we'll learn something about its composition from the onboard instruments and so on. And we won't learn the level of detail we're learning from Bennu because we have the sample in hand, but we'll still learn a tremendous amount. And like I say, all of this is extra science we're getting without having to build a whole new rocket and a whole new spacecraft. So it's great.
Now, clearly some of the data that you've retrieved so far sort of is used to talk about potential life and panspermia or whatnot. But a lot of the information and data will help us to understand how solar bodies can form. Can you explain how you can make models, or how that data can contribute to that idea? And specifically, what are pre-solar grains?
Okay, so so the solar system formed about 4.5 billion years ago, and we think it formed because there was a collapse of a chunk of interstellar dense molecular cloud that collapsed down and started to form the sun, and it formed a disk of material around it. And then this disk collapsed to make the various planets, and a lot of the material was just blown away and left. And then after that 4.5 billion years, we had the planets, and we had small bodies like comets and asteroids, and then things have been slowly evolving since that time. But this material that collapsed down into the disk contained dust grains in it that predated our solar system, that were formed either in the dense molecular cloud that preceded us, or even before that. Stars in space have interesting lives, and some of them blow up at the end of their lives, and some of them shed a lot of material at the end of their lives. And this material gets out into the wide open spaces of the galaxy, and then ultimately gets incorporated into these clouds of dust and ice from which new stars form. And so some of these grains can be ejected out of, let's say, a supernova, float around in space for a long time, get in a dense cloud, end up in an area that's going to start to collapse and make the next planetary system. And if the grain can survive all of that without being wiped out, it can end up in a parent body like Bennu and be sitting in our sample as an individual grain that's not as old as the solar system. It's older than the solar system. And we know this is the case because we can find grains where we can measure the isotopic ratios of some of their elements, what the different masses of the element are present in isotopes, and demonstrate that they're not like the solar systems, that they're different from our entire solar system. And in fact, we can even match those to what we expect the ratios to be coming out of things like supernovas. So we can hunt for grains in the meteorites and in the return samples. They're rare. They're only, present in parts per million usually, but that are older than the solar system and show nucleosynthetic signatures of having come from pre-existing stars that were around before our solar system was even a gleam in the galaxy's eye. And so these grains are super interesting because they tell us all about nucleosynthesis and other stars. But they're also interesting from the sampling perspective because the fact that the grain could get into, let's say, an object like Bennu and survive for us to measure put some constraints on the environments that the grain saw, including the environments it saw on Bennu. So if Bennu had gotten too hot, or if its fluids were too acidic or something like that, some of these grains would have been destroyed and we wouldn't be seeing them. So this puts some constraints on the environments that were on the Bennu parent body as Bennu formed and then subsequently evolved prior to our showing up and stealing a bit. So
do we know for sure that Bennu originated in our solar system?
Yeah, so most of the isotopic abundances of the things we see are perfectly compatible with them being solar system objects. The chemistry and composition all tell us that it probably formed some distance out from the sun, probably maybe out around where maybe Saturn is, or beyond where Saturn is now, because we see plenty of evidence that when the Bennu parent body coagulated, formed together, accreted, that it wasn't just a bunch of high temperature minerals, but we had a lot of volatiles. We got ices at the same time we got grain. So this tells us the temperatures were low where Bennu formed. And in fact, we have plenty of evidence that these ices weren't just ices of water, but were ices of things like carbon dioxide and ammonia. So things that have to be even colder than 0 degrees centigrade to freeze. They have to be very cold. And so that really is a strong indication that Bennu, when it accreted together, was quite far from the sun. And then as the parent body evolved and warmed up after the dust and dispersed, and we ended up with a single object exposed to the sun and had radioactive nuclides inside decaying to slowly warm it up, all of these ices started to melt, and that then caused aqueous alteration. So the majority of this material in this object in the Bennu is consists of a kind of mineral called phyllosilicates, and these are clay minerals, like we make pots out of.
Interesting.
And these kinds of minerals are made when you expose minerals to water and they alter to make the clays. And the vast majority of the material in the samples is returned are these phyllosilicates. So this tells us the Bennu parent body not only accreted a lot of very volatile volatiles and ices, but it also these then melted and for a time, much of the material was exposed to things like water and ammonia and CO2. And these altered the minerals, may have played a major role in the formation and alteration of organic compounds. The water is particularly potentially important for making many of the organic compounds. I mean, when you read a biochemistry text, they always have an equation about molecule A plus molecule B.
Sure.
Arrow gives you C and D. But what they don't mention is that over that arrow is a whole bunch of water.
Yes, of course.
I mean,
and in fact, you found water infused into the clay-like material.
Also, in fact, a phyllosilicate structure contains as a component OH bridges that hold layers of the mineral together. And so water is actually used to make it. But also phyllosilicates are very good at absorbing water and holding on to water. I mean, this is why you put talcum powder in your shoes, is because that's a phyllosilicate, and talcum powder absorbs moisture.
Right, or on the wine stain on the carpet.
Yeah, exactly. Yeah. Right. Yeah. And so the presence of these minerals tells us that Bennu definitely had a period of its early history when fluids were around and volatiles and liquids were around. One of the papers that caused all the excitement recently was one about how we've detected a whole series of minerals which tell us not only that things got wet, but that we made things as things dried out. We have an evaporation sequence as minerals formed in the presence of water that used up some of the water, and the remaining residual water had a different composition because there were some parts of the water fluid we didn't use to make the first mineral. So now we make a new mineral, and then the fluid changes its composition more, and now we make a new mineral. And so as you do this, you end up with a brine. I mean, if you go to a place like Mono Lake or Salt Lake, Great Salt Lake, you've got a fluid which is evaporating, and it's leaving minerals, salts and gypsum and things like this are out, and the brine is concentrating. And we see evidence from a whole series of minerals that this process happened on Bennu. And so Bennu got wet, but then it slowly dried out, and we got chemical activity during all phases of that process. And so any organics that were around would have been exposed to that change in environment, and that change of environment may have helped play a role in making some of the organics, or at least altering them.
Turning away from Osiris for a second, if you could peek at any other place in the universe for signs of life, what would be the most fascinating place that you could go, hypothetically?
Oh God! Well, that's such a vast area, but I mean, so I think in some respects, what would be the most interesting for me would be to go to a place where, if you find life, it's going to be in some way kind of coolly different from what we have. So, in other words, not go to another planet that has an ocean on the surface, kind of like the Earth probably had, etc. But to see if you couldn't expand the kinds of environments where you would find out life exists. So there was this idea for a long time that you have a habitable zone, which is a kind of Goldilocks region where you're not too close to the sun and you cook, and you're not too far away from the sun and you freeze, and that you need to be in that zone. But we're more sophisticated now, and we realize that there are all of these subsurface oceans on the icy outer satellites in the solar system, and that it's conceivable life could exist underneath the surface, and that's well outside the habitable zone for solar heating. And so it'd be fascinating if we could determine that there's life in environments like that, because that vastly expands the scope of the kinds of environments in which you could conceive there could be life. I mean, you can think of stars where there kind of is no great place to be exposed to the star because it's shooting out hard radiation or whatever, but that if you had a giant planet with an icy satellite around it, life might still be able to get started even there. So some of these icy moons environments, which NASA is very, very interested in and working on,
we've got Europa Clipper.
Real interest. And so I would I find that stuff really interesting. I'm not going to be able to participate in any of those missions, but I pay close attention and can't wait to hear what the results of those are. So, so that's expanding into a new zone in a sense. And so obviously a lot of people are interested in whether Mars harbored life. I've played a little role in that in the sense that I've gone to Antarctica I've been to Antarctica 3 times to collect meteorites with the ANSMET program, and I was on the team that found Allen Hill's 84001, the Martian meteorite that was suggested to show signs of life. I'm not convinced by the arguments, but it certainly excited a lot of discussion, and certainly it's completely plausible that Mars could have had life and maybe even still does if you can find the right protected area.
Right.
And so looking for that there is clearly of great interest too. I would, for me personally, I'd rate it a little bit lower, maybe just because it would be this same kind of processes that might have got us started that happen on the Earth. So there isn't that extra bit of novelty. But frankly, finding life anywhere is a game changer, because we go from a case of one, and maybe this is an incredibly weird, rare event, to maybe this is not so uncommon. So finding it anywhere would be of huge interest. I can't name the person for the quote, but somebody said, if there's no other life, if there's life out there, what a huge space for folly. And if there isn't any other life out there, what a tremendous waste of space.
Right. Yeah.
So I think finding other life would be fascinating, because we would learn so much, not only from the things that were the same, but also probably more from what things are different.
Let me ask you, just as we wrap up here, ask you about your early life. As I understand, you grew up in Los Alamos.
Yeah, Los Alamos, New Mexico.
What was it? What was it like growing up in a place, in the shadows of some of the greatest science ever done? You've got Trinity.
So first of all, I'll object to your wording a little bit. I don't feel like I ever grew up in anybody's shadow.
No.
So in Los Alamos, so I think any kid who grows up thinks that where they grow up is the way everybody grows up. So nothing seems unusual about it to you when you're growing up. It's just where things are. And I don't think I really appreciated that Los Alamos was sort of unique until I went off to college, actually. And then I started to realize that my experiences were different from most other people in at least some respects. A lot of it's the same. I still had a bike, I had a dog, But I also, my friends' parents and my parents worked doing really wild things, and many of which they couldn't talk about. My dad never talked about what he did, so I know what he did. Sure, I knew the famous physicist Nicholas Metropolis, but I didn't know him as a famous physicist. I knew him as Kate's dad. And so, like I say, I didn't really particularly feel like I was in anybody's shadow, but I had this advantage of this vast knowledge and interest in the universe around me, and that sort of tinged everything around me. So, my high school was a great high school because many of the teachers were people who had at one point or other worked for the labs and decided they wanted to teach now. And so I learned physics from people and math, from people who had PhDs and knew their stuff. And also, since it was Los Alamos, I'm not sure I understood the concept of a nerd until I went off to college, because being interested in that kind of stuff was perfectly logical, acceptable, normal thing. And so, we had jocks, but we didn't have nerds that were looked down on in any way. It was just another thing to do. And so I left Los Alamos with a real appreciation and fascination with science. I knew I was going to be a scientist long before I left. The public library was a public library, but it had I think 14-volume book on nucleosynthesis, all of which I read in junior high. And so science was a real thing that real people did. And I learned that when I was at Los Alamos, and I took that with me, and that was a huge bonus. And then I got summer jobs working at the lab. When I was an undergraduate, I came home in the summers to work at the Los Alamos Meson Physics Facility Linear Accelerator and do pion cancer therapy and proton tomography and muon scattering experiments with people, and everybody was interested in their work and happy to get others involved. And so I never had a sense of being shouted by anybody. Instead, I felt like they were all shining on me.
Yeah, no, I apologize. You're right. I didn't mean that in any sort of negative way, but just to to absorb that energy and that history must have been absolutely fascinating.
Yeah, and so I still occasionally ponder the fact that my upbringing was in some ways quite bizarre. But it was all of benefit to me, and I was just surrounded by fascinating people doing fascinating things. And then the real wonder of it all was that by the time I got to college, I was able to actually participate in some of that,
Right.
even before I started doing it at a university, which is the more traditional place to start doing research. So it was. I consider myself to be a very lucky person to have had that advantage, but I do remember when I went to high school, 2 junior highs joined there, and I made a new friend who I was fascinating to learn. His father was the town florist. And I went home all excited and told my mom that I'd met a guy whose father was the town florist, and how novel is that? That was,
Not a scientist.
well, for me,
right?
that was exciting.
Yeah, interesting. It's all about perspective, isn't it?
His father wasn't a physicist or a mathematician. And I can remember effusing to her for some time about how interesting this was.
What would you say to young scientists coming up nowadays? I've always had this impression, and maybe incorrectly, that the sort of projects that you're working on, all the missions that you've been a part on, there's not that many of them, and so the opportunities to get involved are slim. Despite, on the flip side, there's lots of people involved in each one of these missions, right? So what would you say to a young scientist, whether they're biologist, engineer, physicist, coming up that ultimately wants to get involved in something like this? What's your advice to that young student?
Well, it's a little hard to be very specific because the branch or the division I work in here at NASA, it does this nice thing where once a month they interview one of the scientists and they go through their whole careers and history, where they grew up and all that. And it's fascinating reading, because when you read these, you find out that nobody working around or near or with me followed a path that's even vaguely like each other or me. They're very wandering paths that take people to a lot of different things, and it's the nature of science that you don't gain an expertise in one thing and then do that for 40 years. You're constantly evolving what you're working on, because science is moving forward. And, once you understand something, you don't spend time studying that anymore. You move on to the next thing. So one of the main things I tell students is learn how to learn. Learn how to teach yourself, because you can go get your degree, your bachelor's or your master's or your PhD, but then when you go out into the real research world, the learning doesn't stop. That's what research is learning. And so you're going to have to learn how to teach yourself. You won't have someone to hold your hand and give you a textbook. So you need to learn how to be your own teacher. And so that's important. And then the other thing is, as you mentioned, missions like the OSIRIS-REx mission involve a lot of people. And one of the reasons it involves a lot of people is you need a lot of very varied expertise. And so to be involved in a mission, it helps for you to build up a personal toolbox of expertise. Learn techniques, become an expert in things that are going to be useful to missions, because that's one of the easiest ways to get involved, is to be able to show up and say, I know how to do that. And so, the OSIRIS-REx mission needed people like me to do the sample science, needed people who had experience with previous sample return missions, because I had a good sort of grandfatherly advice to give on things that worked and didn't work and so on. But the mission needed navigators, and I didn't help with that at all. Okay. Right. And the mission needed engineers who had to build a comm system that worked all the time and was safe and had a battery that would last the right number of years and all that. And I didn't have anything to do with that either, So there are a lot of ways to get involved, and they're not just learning to be on the science side.
Right.
And so you need to find your interests, find the things that fascinate you, and then take advantage of learning as much as you can in those areas. And then you need to be open to opportunities. You never know what's going to come down the pike. And so, I mean, just to use my own experience, I grew up in Los Alamos. I worked at a linear proton accelerator in the summers. And then I earned my way as an undergraduate through college by working for seismologists locating earthquakes all around the Southwest. Then came back in the summers to do tomography and pion cancer therapy at Los Alamos. And then I went to Washington University, where I studied interplanetary dust particles and meteorites. And then I came out to Ames to help them set up the astrochemistry and astrophysics lab, where I worked on radiation processing of weird ices, and then got involved in the Stardust mission. And from then on, because there are so few of us, I was, for better or worse, something of an expert at that. And that got me involved in many of the other missions. And it's just sort of gone from there. So, would I advise that people go get a job at a linear accelerator and then go work for seismologists in order to join the mission? No. The way to do it is to take advantage of the opportunities you get and learn as much as you can and gain as many skills as you can and be ready for the next opportunity. And hopefully that will all, and be aware of the opportunities that are going to lead in the direction you're most interested in, of course, and take advantage of all of that. And hopefully you'll also find good mentors. It always helps to have people around who already have some skills and are happy to invest some of their energy in getting the next generation ready to go. So when you find good people, work with them. That's always good advice for anything, I think.
Absolutely.
And then hopefully it'll all work out. So I think when I talk to students about this, they always leave looking a little puzzled because they were, I think, maybe ultimately hoping I had a formula.
Oh, there's no formula.
Do this and do this and do this. And there is no formula, but there are things you can do to very much help you along your way. So a lot of the work I do in my lab is associated with astrobiology, the whole making of organic compounds by non-biological processes to explore the origin of life. And my lab group over the years, I've had postdocs come in who had their degrees in astronomy, who had their degrees in chemistry, who had their degrees in physics. So all of these bring skills to the work that can be used to help further the goals of the whole team. And so this is a good thing. If your passions are in different areas, that doesn't necessarily preclude you from being able to get involved, because you need people to be involved from all over the place.
And you're ultimately greater than the sum of the parts when you work as a team like that.
Yeah. So, I mean, I did a lot of cool things for OSIRIS-REx, but I would be the last one to tell you that it would have happened with just me.
Right.
I mean, there are hundreds, if not thousands of people involved. They all played key roles. I'm so happy I got to work with all of them. And it only worked because we all worked together, worked very hard over a long time together and made it happen.
That's a wonderful place, I think, to put a bow on it. Dr. Sanford, this was a fascinating discussion. It's an honor to speak with somebody on the ground floor with such a inspiring mission. And I hope and wish you the best of luck in all future missions.
Thank you. I'm always happy to talk science.
Thank you.